What if everything we thought we knew about the origins of galaxies and cosmic structures was just the tip of the iceberg? Picture this: the universe as a vast, intricate tapestry, woven not just by gravity, but by forces so strange, so utterly unexpected, that they defy our most fundamental understanding of reality. This isn't science fiction. It's the cutting edge of astrophysics, where theories once dismissed as wild speculation are now shaking the very foundations of cosmology. From invisible threads of dark matter stretching across the cosmos to quantum fluctuations birthing entire galaxies in their wake, the universe is far weirder, far more mysterious than we ever imagined. Think about the last time you looked up at the night sky, marveling at the glittering expanse of stars. What you're seeing is just a fraction of the story, a fleeting glimpse into a cosmic drama playing out on scales so vast they're almost incomprehensible. Behind those shimmering lights lie secrets that could rewrite the textbooks, phantom energy pushing the universe apart, holographic realms where our 3D reality is just a projection, and cosmic strings, celestial filaments so dense they could warp space-time itself. These aren't just abstract ideas, they're clues to the greatest puzzle of all. How did everything from the tiniest atom to the grandest galaxy come to be? That's exactly what we're about to explore. Over the course of this journey, we'll uncover 23 radical concepts that challenge the very fabric of our understanding. Some will sound like they're straight out of a physicist's wildest dreams until you see the evidence stacking up. Others will make you question whether we've been looking at the cosmos all wrong. But one thing's for certain: by the time we're done, you'll never see the universe the same way again. So buckle up. We're diving deep into the unknown, where the rules of reality bend and the mysteries of existence await. Let's start with the first radical concept, the idea that the entire cosmic web, every galaxy, every cluster, every filament of matter stretching across the universe might trace its origins back to quantum fluctuations tinier than an atom. Picture the early universe, a fraction of a second after the Big Bang, undergoing a mind-bending expansion known as cosmic inflation. Space itself stretched faster than light, magnifying those infinitesimal quantum ripples into the seeds of everything we see today. But here's where it gets wild. What if inflation wasn't smooth? Some theories propose it was chaotic, a turbulent storm of expanding space where different regions inflated at different rates, even with different physical constants. Imagine bubbles of reality, each a universe unto itself, with laws of physics utterly alien to ours. Our observable cosmos, with its delicate balance of forces allowing stars and planets, and life, to exist, could be just one lucky pocket in an infinite multiverse. Now think about the implications: the distribution of galaxies, the voids between them, even the way matter clumps together. None of it would be random. Instead, it'd be the frozen imprint of quantum randomness writ large, a cosmic fingerprint from the universe's first moments. Recent simulations show how these quantum seeds, stretched by inflation, could evolve into the vast cosmic web we observe today. But what if we're seeing only part of the picture? Some models suggest that if inflation was chaotic, our universe might be brushing up against others, their gravity subtly warping the structure of our own cosmos. It's a humbling thought. The grand tapestry of galaxies might be woven not just by the laws we know, but by forces beyond our current understanding. This isn't just speculation. Telescopes like the James Webb are now peering into the early universe, hunting for anomalies in the distribution of galaxies that could hint at these primordial quantum ripples, or even evidence of collisions with other bubble universes. If confirmed, it would mean that the very fabric of reality is far stranger, far more interconnected than we ever dared imagine. So the next time you gaze at the night sky, remember, those stars aren't just points of light. They're the echoes of quantum whispers from the dawn of time, stretching across eternity. But here's where it gets even more fascinating. Dark matter isn't just some passive bystander in the cosmos. It's the unseen architect, the invisible hand that sculpted the universe into the intricate web we see today. Imagine a vast cosmic blueprint where dark matter's gravity drew the first faint outlines of structure long before stars or galaxies even existed. Supercomputer simulations reveal something astonishing. Without dark matter's gravitational pull, ordinary matter would have been too scattered, too chaotic, to ever clump together into the galaxies and clusters we recognize. It's as if dark matter laid down the scaffolding and everything else, stars, planets, even us, simply followed its lead. Yet the more we learn, the stranger this hidden framework becomes. What if dark matter isn't just one thing? Traditional theories describe it as a single type of slow-moving particle, but alternative ideas are turning that assumption on its head. Some scientists propose that dark matter could decay over time, subtly altering the way galaxies form. Others suggest it might interact with itself through unknown forces, creating intricate dynamics that reshape cosmic structures in ways we're only beginning to model. Picture a hidden dance of particles, governed by rules we can't yet see, influencing everything from the shape of spiral galaxies to the distribution of colossal galaxy clusters billions of light-years apart. And here's the real kicker: dark matter's secrets might rewrite the entire timeline of the universe. If its properties are more complex than we thought, it could mean that galaxies assembled earlier or later than our current models predict. Recent observations of surprisingly mature galaxies in the early universe, spotted by the James Webb Space Telescope, are already raising eyebrows. Could these cosmic anomalies be hints that dark matter played a different role in the universe's youth than we ever anticipated? The answer could reshape not just our understanding of the past, but the fate of everything that lies ahead. So while dark matter remains invisible to our telescopes, its fingerprints are everywhere, in the graceful arcs of galaxy clusters, the delicate threads of the cosmic web, even in the very rhythm of the universe's expansion. The mystery isn't just about what dark matter is, but how it shaped the stage for our existence. And with every new discovery, we're peeling back another layer of this cosmic enigma, one invisible thread at a time. What if some of the universe's most mysterious objects, black holes, weren't just cosmic destroyers, but builders? Imagine a scenario so counterintuitive that it rewrites the cosmic rulebook. Black holes existing before stars, before galaxies, even before light itself had fully escaped the newborn universe. These wouldn't be the black holes we know today, born from collapsing stars, but something far more exotic: primordial black holes, forged in the unimaginable pressures of the Big Bang's first moments. Theorists propose these ancient behemoths could have acted like gravitational seeds, pulling matter into dense knots that eventually grew into the galaxies we see today. It's a staggering idea. The very structures we thought took billions of years to assemble might owe their existence to black holes that were there from the beginning. The implications are mind-bending. If primordial black holes existed, they wouldn't just be relics, they'd be active players in shaping the cosmos. Picture a universe still in its infancy, filled with swirling clouds of gas and dark matter. A primordial black hole, even one no heavier than a mountain, would exert an outsized gravitational pull, drawing material toward it like a cosmic magnet. Over time, these pockets of matter could have grown dense enough to ignite the first stars, birthing the earliest galaxies in their wake. Some simulations even suggest that these black holes could explain why galaxies formed so quickly in the universe's youth, a puzzle that's puzzled astronomers for decades. But here's where it gets truly strange. Unlike the black holes we observe today, which emit telltale X-rays as they devour matter, primordial black holes could be nearly invisible, dark shadows lurking in the voids between stars. Some might still be out there, drifting unseen through our galaxy, their presence betrayed only by subtle distortions in starlight or mysterious gravitational tugs on nearby objects. Even more intriguing, they could solve another cosmic mystery, dark matter. If enough of these primordial black holes survived, their combined gravity might account for the missing mass we've been searching for all along. The hunt for proof is already underway. Telescopes are scanning the skies for the fleeting flashes of light that would occur if a primordial black hole passed in front of a distant star, bending its light like a lens. Other researchers are listening for the faint echoes of gravitational waves, ripples in space-time that could reveal collisions between these ancient objects. If even one is found, it wouldn't just confirm a radical theory, it would rewrite the story of how our universe took shape. Because if black holes were the architects of the cosmos, then the night sky isn't just a collection of stars. It's a monument to the unseen builders that sculpted it from the darkness. What if the three-dimensional universe we perceive, with its swirling galaxies, vast voids, and intricate cosmic web, is nothing more than an illusion? The holographic principle turns our understanding of reality inside out, proposing that everything we see, from the smallest atom to the largest supercluster, might be a projection from a two-dimensional surface at the edge of the cosmos. Think of it like a movie. The images on the screen appear lifelike and three-dimensional, but they're actually encoded on a flat, two-dimensional film. In the same way, the universe's staggering complexity could be a grand illusion, with all the information needed to build it stored on a distant boundary we can't even see. This isn't just a wild thought experiment, it's a serious theory with roots in black hole physics. When scientists studied the behavior of information falling into a black hole, they made a startling discovery. The amount of information that can be stored inside isn't determined by its volume, but by the area of its event horizon, the two-dimensional surface marking its point of no return. This bizarre connection between surfaces and the space within them led physicists to ask a revolutionary question: could the entire universe work the same way? If so, the origin of cosmic structures wouldn't lie in the depths of space, but in the way information is woven into the fabric of reality itself. Imagine the universe's birth as a cosmic printer, etching the blueprint for galaxies, stars, and planets onto a two-dimensional surface at the edge of existence. Over time, that information projects inward, creating the three-dimensional world we inhabit. This could explain some of the universe's most puzzling features, like why it appears so finely tuned for complexity. If the laws of physics aren't inherent to space but emerge from deeper, two-dimensional rules, it might mean the universe's structure was never random. It was always encoded, waiting to unfold. The implications are staggering. If the holographic principle is correct, then the cosmic web, those vast filaments of galaxies stretching across the void, aren't just physical structures. They're shadows of information, echoes of a deeper reality we're only beginning to glimpse. Even time itself might be part of the illusion, a side effect of how that two-dimensional data is translated into our three-dimensional experience. It's a humbling thought. Everything we consider solid, real, and permanent could be nothing more than a hologram, flickering into existence at the boundary of the unknown. And here's the most tantalizing part. This isn't just philosophy. Experiments are underway to test the holographic principle, using precision instruments to hunt for subtle pixelation in space-time. Tiny, grain-like fluctuations that would betray the universe's true two-dimensional nature. If they succeed, it would mean our search for the origins of cosmic structure has been looking in the wrong dimension all along. The answers might not be hidden in the depths of space, but written on the surface of reality itself, waiting for us to decode them. Dark energy already poses one of cosmology's greatest mysteries, an invisible force pushing the universe apart at an accelerating rate. But what if that force isn't just constant? What if it's growing stronger over time, a runaway effect with the power to unravel the cosmos itself? This is phantom energy, a hypothetical form of dark energy so extreme, it could make the universe's expansion not just continue, but spiral out of control. Imagine a future where galaxies, stars, even atoms are torn apart by the relentless stretching of space itself. Yet the real shock isn't just what phantom energy could do to the universe's fate, but what it might have already done to its past. Rewind to the universe's infancy when the first seeds of cosmic structure were forming. Most models assumed dark energy played a minor role back then, its influence dwarfed by gravity's pull. But phantom energy flips that script. If it existed in the early universe, even in fleeting bursts, its repulsive force could have supercharged the growth of galaxies and clusters. Picture a cosmic tug of war, gravity trying to pull matter together, while phantom energy's push creates dense regions where matter collapses faster and voids where it's stretched thinner. This might explain why some patches of the universe are eerily empty, vast bubbles of nothingness far larger than our theories predict. The evidence is tantalizing. Astronomers mapping the cosmic web have noticed strange gaps, regions where galaxies are suspiciously scarce. Could these be scars from phantom energy's fingerprints, ancient fluctuations that left parts of the universe stretched thin? Simulations show that if this energy varied across space and time, it wouldn't just accelerate expansion, it would sculpt the distribution of matter in ways that match these puzzling observations. And here's the twist: phantom energy's influence wouldn't stop at shaping structures. It could rewrite the timeline of galaxy formation, compressing billions of years of evolution into a frenzied burst of activity. But the most unsettling possibility lies ahead. If phantom energy exists, it doesn't just hint at a strange past, it foretells a violent end. Unlike ordinary dark energy, which pushes galaxies apart gently over eons, phantom energy grows stronger with time. In a future tens of billions of years from now, its grip could become so overpowering that it rips apart galaxy clusters, then individual galaxies, then stars, planets, and finally the fabric of space-time itself. This apocalyptic scenario, known as the Big Rip, isn't just theoretical. Certain measurements of the universe's expansion already align disturbingly well with models that include phantom energy's explosive growth. Yet for all its destructive potential, phantom energy might also hold the key to understanding one of cosmology's deepest puzzles: why the universe's expansion is accelerating in the first place. If this energy fluctuates, it could mean that what we call dark energy isn't a single, unchanging force, but a dynamic phenomenon with phases of intensity. Some theories even suggest it's tied to exotic fields or undiscovered particles, relics from the Big Bang that briefly surged during the universe's formative moments. Right now, telescopes are hunting for clues, subtle distortions in the cosmic web, unexpected patterns in the distribution of galaxies, or anomalies in the way light bends across the void. Each observation could bring us closer to confirming whether phantom energy is real or ruling it out entirely. But one thing's certain: if it exists, our understanding of cosmic structure and the universe's ultimate fate will need a radical rewrite. The same force that might one day tear everything apart could have been the hidden architect of the cosmos all along. Picture the early universe not as a silent void, but as a cosmic symphony, a seething plasma where sound waves rippled through the hot, dense soup of particles like echoes in a cavern. These weren't ordinary sound waves, but pressure oscillations so powerful they left permanent scars in the fabric of spacetime itself. Today, billions of years later, we see their fingerprints etched into the universe's structure, galaxies clustered at precise intervals as if spaced by an invisible hand. These are Baryon acoustic oscillations, the universe's ancient heartbeat frozen in time. Think of BAOs as cosmic yardsticks. Just as a ruler's markings let you measure distance, these oscillations provide a fixed scale about 500 million light-years across that astronomers use to gauge the universe's expansion. By comparing how these ripples stretched over cosmic history, we've uncovered dark energy's relentless push. But here's the twist: what if these oscillations aren't just rulers? What if they're encrypted messages from the universe's first moments, hinting at forces we've yet to discover? Some theories suggest that dark energy wasn't always the gentle force we observe today. In the universe's infancy, it might have surged in fleeting bursts, a phenomenon called early dark energy. This temporary surge could have altered the way BAOs propagated, subtly warping their spacing in ways that linger in today's galaxy distributions. Imagine throwing a pebble into a pond, only for an unseen current to bend the ripples mid-spread. That's the kind of anomaly astronomers are hunting for, tiny deviations in the expected pattern of galaxies that could betray dark energy's wild youth. Then there's the possibility of extra dimensions. If our universe is embedded in a higher dimensional space, like a sheet of paper floating in a vast room, gravity could have leaked into those dimensions during the BAO's formation. This leakage would have weakened gravity's pull just enough to tweak the oscillation's final imprint. The result: galaxy clusters spaced slightly farther apart than our models predict, a ghostly sign of dimensions beyond our perception. The hunt for these anomalies is already reshaping our tools. Projects like the Dark Energy Spectroscopic Instrument are mapping millions of galaxies with unprecedented precision, searching for telltale distortions in the BAO pattern. Even the slightest irregularity could rewrite our understanding of cosmic history, revealing whether dark energy played by different rules in the past, or if hidden dimensions once tugged at the fabric of reality. So the next time you hear about the cosmic web, remember, it's not just a static map of galaxies. It's a fossil record of the universe's earliest vibrations, a symphony written in the language of gravity and light. And somewhere in those celestial harmonies, there may be notes we haven't yet learned to hear, clues to forces that shaped everything, then vanished without a trace. Some of the universe's most bizarre structures might owe their existence to cosmic strings, threads of pure energy so thin, they're effectively one-dimensional cracks in spacetime. Imagine the early universe cooling from its fiery birth, like molten glass hardening into crystal. As it transitioned, imperfections could have formed not tiny bubbles or cracks, but ultra-dense filaments thinner than a proton yet stretching across the entire cosmos. These aren't just theoretical oddities. If they exist, cosmic strings would carry unimaginable tension, warping space-time around them so fiercely that their gravity could have spun the first galaxies into being like beads on an invisible wire. The math behind them is staggering. A single cosmic string just 1 light-year long might weigh as much as an entire galaxy, yet be so narrow you could pass right through it without noticing. Their gravitational influence would be anything but subtle, though. Picture a string slicing through a cloud of primordial gas, its immense density creating shock waves that compress matter into dense knots. Over millions of years, those knots could collapse into stars, then galaxies, all strung along the cosmic filament like pearls. This might explain why astronomers keep finding galaxies aligned in vast, thread-like formations, as if drawn together by some unseen force. Here's where it gets even stranger. Unlike black holes or dark matter, cosmic strings wouldn't just sit there, they'd vibrate. Any kinks or loops in these space-time cracks would whip around at near light speed, sending out ripples in the fabric of reality itself. These gravitational waves would be unlike anything from colliding black holes. They'd carry a distinct, high-pitched signature that detectors like LISA or pulsar timing arrays might soon catch. If they do, it wouldn't just confirm cosmic strings exist. It could mean we've spotted the spinning wheels that wove the cosmic web, but the wildest possibility. Some cosmic strings might still be out there, not fossilized relics, but active, vibrating threads humming through the void. If one passed through our solar system today, it wouldn't tear planets apart, but it would leave a ghostly fingerprint. Clocks might briefly tick out of sync, or light from distant stars could flicker as space-time itself stretches and rebounds. There's even a chance, however small, that we've already seen their handiwork. Certain oddities in the cosmic microwave background, the afterglow of the Big Bang show patterns that look suspiciously like strings, might have brushed against them, leaving wrinkles in the universe's oldest light. So while cosmic strings remain hypothetical, their potential to rewrite cosmic history is undeniable. They could be the missing architects behind the universe's large-scale structure, the hidden hands that spun galaxies into place. And if we ever detect their gravitational whispers, it would mean the cosmos wasn't just built by gravity and dark matter, but by flaws in the very fabric of reality, frozen in time from the universe's first desperate moments. What if the Big Bang wasn't the beginning, just a violent chapter in an endless cosmic cycle? The Ekpyrotic universe theory turns conventional cosmology on its head, proposing that our universe was born not from a single explosive moment, but from the collision of two vast, higher-dimensional membranes called branes. Picture these branes as infinite sheets floating in an 11-dimensional space, separated by a gap so tiny it's unfathomable. When they finally smashed together, the energy released didn't just ignite our universe, it imprinted it with the seeds of all cosmic structure. This isn't just a wild alternative to inflation, it's a radically different origin story. In the Ekpyrotic model, those primordial density variations, the ones that eventually grew into galaxies and clusters, weren't magnified quantum fluctuations. They were wrinkles left by the branes themselves, like fingerprints pressed into clay. The collision would have been chaotic, sending shockwaves rippling through the newborn universe, but with a key difference. Unlike inflation's rapid stretching, the Ekpyrotic scenario predicts a slower, more controlled expansion. The result, a cosmic web with fewer extreme variations. No gargantuan voids or ultra-dense superclusters, just a smoother, more even distribution of matter. Here's where it gets even more mind-bending. If the branes are still out there, drifting in higher dimensional space, they could collide again. Not just once, but endlessly, in an infinite cycle of cosmic destruction and rebirth. Our universe might be one page in an infinite library of universes, each born from its own collision, each with slightly different physical laws. Some might be lifeless wastelands, others could harbor conditions even more perfect for complexity than our own. And if the cycle repeats, it raises a haunting question. Could traces of a previous universe still linger in ours? The hunt for evidence is already underway. The Ekpyrotic model leaves subtle fingerprints, a distinct pattern of gravitational waves, for instance, quieter and lower in frequency than those predicted by inflation. Future observatories like the Laser Interferometer Space Antenna might soon catch these whispers from the dawn of time. another clue lies in the cosmic microwave background. If the branes collided at an angle, they could have imprinted a telltale asymmetry in the universe's oldest light, a lopsidedness that telescopes are now scouring the skies to find. But the most profound implication isn't just about our past, it's about our place in reality. If the Ekpyrotic model is right, then the cosmos isn't a one-time event. It's a symphony of collisions, an endless dance of branes weaving universes into existence. The galaxies we see, the stars we cherish, even the atoms in our bodies might be echoes of a collision that happened unimaginable eons ago. And somewhere in the hidden dimensions beyond our perception, the next universe could already be taking shape, waiting for its turn to burst into being. So while we piece together the fragments of our cosmic origin, remember, the truth might not lie in a single explosive moment, but in the quiet, inevitable approach of two unseen worlds closing the distance until once again everything begins. Imagine a particle so ghostly it can pass through a light year of solid lead without slowing down. Yet with just a whisper of mass, it might hold the key to why our universe looks the way it does. Neutrinos are the universe's ultimate escape artists, streaming from stars, supernova, and the Big Bang itself, barely interacting with anything in their path. For decades, we assumed they were weightless, cosmic phantoms with no role in shaping galaxies. But what if we've underestimated them? Even the tiniest mass, multiplied by the countless trillions of neutrinos flooding every corner of space, could have subtly steered the formation of cosmic structure in ways we're only beginning to uncover. Take sterile neutrinos, theoretical heavier cousins of the ordinary neutrinos we've detected. Unlike their lightweight relatives, these hypothetical particles wouldn't just slip through matter. They'd barely interact with the forces of nature at all, making them prime candidates for dark matter. Here's the twist: if sterile neutrinos exist, their unique behavior could explain one of cosmology's nagging puzzles: why some galaxies in the early universe look suspiciously young. Picture these heavy neutrinos flooding the cosmos in its first moments, their gravity pulling matter together just enough to seed galaxies, but their odd quantum properties causing them to zip away before structures fully formed. The result, a cosmic slowdown, delaying star formation and leaving some galaxies appearing oddly immature compared to their peers. This isn't just speculation. Supercomputer simulations reveal that sterile neutrinos would leave a distinct imprint on the universe's architecture. Their tendency to free stream away from dense regions would suppress the growth of small clumps of matter, leading to fewer dwarf galaxies than predicted, a mismatch astronomers have actually observed. Even more intriguing, sterile neutrinos could decay, emitting faint X-rays that might explain mysterious signals detected from distant galaxy clusters. It's as if the universe left us breadcrumbs, hints of a hidden particle that bridges the gap between ordinary neutrinos and the dark matter we've been chasing for decades. But the real revolution lies in what this means for dark matter itself. For years, we've assumed it's made of a single, sluggish particle like the WIMP. Sterile neutrinos shatter that assumption, suggesting dark matter could be diverse, a shadowy family of particles with different masses and behaviors. Some might be heavy and slow, others nearly as light as ordinary neutrinos, but just numerous enough to tip the cosmic scales. This could solve another puzzle: why dark matter seems to cluster differently on small scales than our models predict. If it's partly made of these elusive, fast-moving particles, their ability to smooth out small fluctuations would perfectly match the universe we see. The hunt for proof is already pushing technology to its limits. Underground detectors are monitoring ordinary neutrinos for hints of oscillation into their sterile counterparts, while telescopes scour the cosmos for those telltale X-ray signals. Even the cosmic microwave background might hold clues, subtle temperature variations that betray sterile neutrinos' presence in the early universe. If confirmed, it would mean that the answer to one of cosmology's biggest mysteries wasn't some exotic, undiscovered particle, but a twist on something we've known about all along. The universe's grand structure, from the tiniest dwarf galaxies to the largest superclusters, might owe its existence to particles so faint they've been hiding in plain sight. So the next time you hear about dark matter, remember, the truth might not lie in the shadows, but in the ghostly particles that have been slipping through our fingers since the dawn of time. And if sterile neutrinos are real, they're not just rewriting the story of cosmic structure, they're blurring the line between the ordinary and the unknown, proving that sometimes the most profound secrets are the ones we never thought to question. What if the delicate balance of our universe, the precise tuning of gravity, the exact strength of the nuclear forces, even the amount of dark energy, wasn't the result of some grand design, but a cosmic roll of the dice? The multiverse theory throws open the doors to a staggering possibility. Our universe isn't special. It's just one of countless others, each with its own random set of physical laws. Most of those universes would be barren, their parameters too extreme for atoms to form, let alone stars or galaxies. But by sheer probability, a handful would land on the perfect numbers for structure to emerge, and we, by definition, find ourselves in one of those lucky few. This idea, known as the Anthropic Principle, flips the script on how we think about cosmic origins. Instead of asking why our universe is fine-tuned for complexity, we're forced to confront a humbling truth: it might not be tuned at all. Imagine walking into a casino with 1 billion slot machines, all spinning at once. Nearly every machine lands on a losing combination except one. That's us. The cosmic web, the glittering galaxies, even the conditions that allowed life to arise aren't evidence of intent. They're the statistical outliers of a vast, indifferent multiverse. The implications ripple through every layer of cosmology. Take dark energy. Its bafflingly small but non-zero value is often called the worst prediction in physics. If it were even slightly stronger, the universe would have torn itself apart before galaxies could form. Slightly weaker, and gravity would have collapsed everything back into a big crunch. In a multiverse, this Goldilocks value isn't a puzzle, it's a necessity. Universes where dark energy deviates from this narrow window simply don't get observers. No galaxies, no planets, no one to wonder why the numbers look so perfect. But here's where it gets even stranger. The multiverse could explain why the cosmic web looks the way it does. In most universes, matter might clump too aggressively, creating a chaotic mess of black holes, or spread too thinly, leaving nothing but vast, empty deserts. Ours sits in a sweet spot where gravity pulls matter into intricate filaments and voids, allowing just enough structure for diversity, but not so much that everything collapses. Simulations of alternate universes show how slight tweaks to the strength of gravity or the initial density of matter would erase the delicate sponge-like pattern we see in galaxy surveys. Critics argue this sounds like giving up, replacing the quest for deeper laws with a shrug of anything that can happen does. But the multiverse isn't entirely untestable. If other universes bubble off from our own, their collisions could leave scars in the cosmic microwave background, faint circular patterns that telescopes might one day detect. Even more intriguing, the distribution of galaxies could betray signs of a multiverse. If our universe's parameters were randomly selected, there might be unexpected statistical quirks in how matter is arranged, subtle fingerprints of the cosmic lottery that birthed us. Yet the most profound consequence isn't scientific, it's philosophical. If the multiverse is real, then every galaxy, every star, every living creature exists against ludicrous odds. The universe didn't have to be this way. It could have been a formless void or a seething chaos. Instead, by a twist of probability, we got a cosmos rich enough to question its own existence. So when you look up at the night sky, remember, those stars aren't just points of light. They're the winning numbers in the ultimate cosmic jackpot, a fleeting alignment of chance that allowed the universe to wake up and behold itself. For centuries, gravity has been the universe's most predictable force, Newton's equations perfectly describing the fall of an apple, and Einstein's relativity capturing the dance of planets. But zoom out to the scale of galaxies and something strange happens. Stars orbit their centers so fast that, by all known physics, they should fling themselves into the void. The solution: dark matter, an invisible scaffold holding galaxies together. But what if we've been looking at the problem backward? What if the flaw isn't in our map of matter, but in our understanding of gravity itself? This is the radical proposition of modified Newtonian dynamics, or MUND. Instead of invoking unseen particles, MUND suggests gravity doesn't fade as quickly as we thought in the feeble pull of a galaxy's outskirts. Picture a river flowing gently downstream until it reaches a hidden rapid where the current surges unexpectedly. In MUND framework, gravity behaves similarly, subtle where we expect it to be strong, then gripping tighter where it should weaken. The result: stars on the edges of galaxies move faster than Newton's laws predict, matching observations without a shred of dark matter. At first glance, the evidence is compelling. MUND accurately predicts the rotation curves of hundreds of galaxies with eerie precision, something dark matter models often struggle with unless meticulously tuned. It's as if we've spent decades inventing invisible dancers to explain a mysteriously swaying stage, when all along the stage itself had hidden springs. Proponents argue this isn't just Occam's razor at work. It's a fundamental rethink of how gravity operates in the cosmic shadows, but the cosmic web complicates the story. Dark matter doesn't just explain galaxy rotations. It's the backbone of the universe's large-scale structure. Supercomputer simulations show how dark matter's gravity sculpts the vast filaments and voids we observe, with ordinary matter simply tracing its contours. Strip away dark matter, and MUND must somehow replicate this intricate architecture under modified gravity alone. Some theorists propose tweaks adding subtle relativistic extensions to MUND, or suggesting that gravity's behavior changes not just with distance, but with the acceleration of the expanding universe itself. These adaptations show promise, but they lack the elegant universality of Einstein's equations, often feeling like patches on a theory still in flux. Then there's the bullet cluster, a cosmic collision where X-ray observations reveal two galaxies have passed through each other, leaving their visible gas behind. The kicker: the bulk of the mass mapped by gravitational lensing isn't where the gas is. Dark matter models explain this neatly. The invisible matter sailed through the collision, while the gas slowed like smoke caught in a breeze. MUND struggles to account for this separation without some form of unseen mass, forcing its advocates to propose exotic neutrino-like particles or other tweaks that edge uncomfortably close to reinventing dark matter in disguise. Yet the debate is far from settled. New theories like emergent gravity, which suggests gravity isn't a fundamental force but a side effect of quantum information on cosmic scales, offer fresh twists on modified gravity. Others explore whether Einstein's relativity might break down in the ultra-weak fields between galaxies, like a compass glitching near a magnet's edge. Meanwhile, telescopes like Euclid are mapping the universe's structure in unprecedented detail, hunting for subtle distortions that could betray gravity's true behavior across billions of light years. The stakes couldn't be higher. If Mund or a successor theory is right, we're on the brink of a paradigm shift as profound as relativity replacing Newton. But if dark matter prevails, modified gravity becomes a beautiful idea that couldn't quite match reality. For now, the universe keeps its secrets close, whispering hints in the spin of galaxies and the weave of the cosmic web, waiting for us to decipher which path leads to the truth. The universe should be loud, with hundreds of billions of galaxies, each hosting countless stars and planets. The cosmic chatter of advanced civilizations ought to be deafening, yet all we hear is silence. This eerie absence of alien signals is the Fermi Paradox, one of science's greatest enigmas. But what if the silence isn't empty at all? What if we've been searching for radio waves when we should have been scanning the stars for something far grander, the fingerprints of civilizations so advanced they've reshaped the cosmos itself? Consider the possibility that extraterrestrial societies don't just inhabit planets, they transform them. Imagine harnessing the energy of an entire star by encasing it in a Dyson swarm, a vast constellation of orbiting solar collectors. Such a megastructure would glow not with visible light, but with the infrared warmth of wasted heat, a telltale signature astronomers have already scoured the skies for. Or picture a civilization moving stars like chess pieces, rearranging their positions to optimize energy capture or even avoid cosmic threats. Over millennia, these manipulations could leave entire regions of space oddly sparse, as if someone had carefully pruned the galactic garden. This isn't just speculation, it's a lens through which some astrophysicists now view cosmic anomalies. Take KBC Void, a colossal bubble of emptiness 7 times wider than expected, where galaxies are conspicuously scarce. Conventional cosmology struggles to explain it, but what if it's not natural? Advanced societies might deliberately clear vast territories to minimize collision risks or create computational substrates cold enough to run unfathomable simulations. Even stranger are galaxies with unusual light curves or missing infrared emissions, features that defy standard astrophysical models but align disturbingly well with theoretical blueprints for stellar-scale engineering. The implications rewrite not just astrobiology but our understanding of cosmic structure. If intelligence can alter the architecture of the universe, then the voids, filaments, and clusters we see might not solely be the work of gravity and dark matter. They could be artifacts, a blend of natural processes and deliberate design, like a forest shaped by both wind and human hands. Some theorists go further, suggesting that what we call dark matter could even be the residue of unimaginable technologies, a shadow infrastructure left by civilizations that mastered physics beyond our comprehension. Yet the most haunting possibility isn't that we're alone, it's that we're late. The universe is 13.8 billion years old, plenty of time for civilizations to rise, expand, and perhaps burn out. The structures they built could now be cold relics, their creators long gone, leaving behind only cosmic ruins for us to stumble upon. Or worse, we might be like ants in a cathedral, surrounded by evidence of intelligence so advanced we lack the tools to recognize it. The search is already shifting. Projects like the Vera Rubin Observatory aren't just mapping galaxies, they're hunting for anomalies that could betray artificial origins. Each oddity, each deviation from the expected, is a potential clue in the universe's greatest detective story. Because if even one of these cosmic irregularities turns out to be the work of intelligence, it wouldn't just solve the Fermi Paradox. It would mean the universe isn't just alive, it's been engineered. What if the universe's structure wasn't just shaped by the push and pull of matter and energy, but by the rhythm of time itself? Time crystals, one of the most bizarre discoveries in modern physics, defy everything we thought we knew about the nature of reality. Unlike ordinary crystals, which repeat their atomic patterns in space, think of the symmetrical lattice of a diamond time crystals repeat in time. Their structure oscillates endlessly like a clock that ticks without ever being wound, locked in a perpetual dance that even the relentless march of entropy can't disrupt. Now imagine these strange objects not just as lab curiosities, but as titanic structures flickering into existence in the seething chaos of the early universe. Their pulses could have sent ripples through the infant cosmos, imprinting irregularities in the density of matter that would one day grow into galaxies, clusters, and the vast cosmic web. The idea hinges on a quantum quirk. Time crystals emerge when a system falls into a state of broken time symmetry. In plain terms, the usual uniformity of time, the fact that physical laws work the same whether you're watching them play forward or backward, gets shattered. Under extreme conditions like those in the universe's first moments, this breaking could have spawned time crystals on cosmic scales. Picture them as colossal, invisible metronomes, each beat subtly nudging the surrounding plasma, creating pockets where matter clumped slightly denser or thinner than average. Over billions of years, those tiny variations would have snowballed into the galaxies we see today, but with a twist. If time crystals were involved, the distribution of matter might carry strange, rhythmic patterns, like echoes of those primordial ticks etched into the sky. Here's where it gets even wilder. Time crystals wouldn't just create random fluctuations, they'd generate oscillations with precise, predictable periods. If they existed in the early universe, their influence could explain why some regions of space show oddly regular spacing between galaxy clusters, almost as if they were stamped out by a cosmic pendulum. Astronomers have already spotted hints of these patterns in large-scale surveys, anomalies that don't quite fit the standard model of inflation. Could they be the fossilized imprint of time crystals that pulsed for a fleeting instant after the Big Bang, then vanished as the universe cooled? The implications reach beyond cosmic structure. If time crystals played a role, they'd forge a direct link between the quantum realm and the grand scale of the cosmos, a bridge between the physics of the unimaginably small and the astronomically vast. It would mean that time itself, not just space, was an active architect of the universe's form, and the echoes of those ancient rhythms might still be detectable today. Future telescopes mapping the distribution of dark matter or the cosmic microwave background could hunt for the telltale signatures of these temporal structures, looking for patterns that no natural process other than time crystals could explain. So while the idea remains speculative, it's a stunning reminder of how deeply strange the universe might truly be. The galaxies above us, the voids between them, even the very fabric of space-time, all of it could bear the hidden fingerprints of a reality where time doesn't just flow, but dances. And if we ever find the proof, it won't just rewrite cosmology. It'll redefine our place in a cosmos where the fourth dimension isn't a passive stage, but a sculptor's chisel, carving the universe into shape one eternal tick at a time. Magnetism seems like a latecomer to the cosmic stage, something that emerged only after the first stars ignited and galaxies took shape. But what if the universe's magnetic fields were there from the very beginning, woven into the fabric of reality during the Big Bang itself? Astronomers have stumbled onto a puzzling phenomenon. Certain galaxies, especially those in the early universe, possess magnetic fields up to 1,000 times stronger than our models predict. These aren't just anomalies, they could be fossils, remnants of a primordial force that helped sculpt the cosmos long before the first stars flickered to life. Picture the universe in its infancy, a seething plasma so hot and dense that particles couldn't even form atoms. In that chaos, quantum fluctuations might have generated magnetic fields on a scale we can barely fathom. not the gentle curves of a bar magnet, but vast cosmic webs of magnetism stretching across the entire observable universe. These fields would have been weak, almost imperceptible, but they didn't need to be strong to leave a lasting mark. Like invisible hands, they could have gently guided streams of charged gas, nudging matter into the filaments and knots that would one day become galaxies. The evidence is mounting. Take the Spiderweb Galaxy, a massive cluster in the distant universe where magnetic fields are bizarrely strong and aligned over staggering distances. Traditional theories struggle to explain how such coherence could emerge so early unless those fields were already there, imprinted in the universe's first moments. Even more compelling are observations of galaxies so young, they shouldn't have had time to generate their own magnetism through stellar winds or black hole activity. Yet there they are, glowing with polarized light that betrays the presence of organized magnetic fields. It's as if the universe handed these galaxies a magnetic blueprint at birth. Here's where the implications get radical. If primordial magnetism existed, it didn't just assist gravity in shaping cosmic structure, it might have accelerated it. Simulations show that even faint magnetic fields can dramatically speed up the collapse of gas clouds, compressing them into dense filaments where stars ignite faster and galaxies assemble sooner. This could solve a long-standing puzzle: why some galaxies in the early universe appear suspiciously mature, as if they had a head start on formation. The answer might not lie in exotic dark matter or unseen forces, but in something as familiar and as mysterious as magnetism. Yet the biggest mystery remains: how could these fields survive the Big Bang's fury? One theory suggests they were frozen into the fabric of spacetime during inflation, stretched to cosmic scales but never entirely erased. Another proposes that quantum effects in the early universe's plasma spontaneously generated magnetism, like sparks flickering in a storm. Either way, if primordial magnetism is real, it means our universe didn't just evolve under gravity's rule, it danced to the pull of invisible magnetic currents, a hidden symphony guiding the birth of everything we see. The hunt for proof is now a race against time. Radio telescopes like the Square Kilometre Array are scanning the deepest reaches of space, searching for the faintest whispers of magnetic fields in regions where no stars yet shine. If they find them, it won't just rewrite the story of galaxy formation. It will reveal that one of nature's most fundamental forces was there at creation, quietly shaping the cosmos from the very first moment. So the next time you hold a compass, remember, its needle doesn't just point north. It's tracing the echoes of a magnetic pulse that may have helped build the universe itself. What if our entire universe, every galaxy, star, and atom, isn't floating in empty space at all, but trapped inside the event horizon of a colossal, higher-dimensional black hole? This isn't just a sci-fi plot twist. It's a serious theory gaining traction among physicists, and it flips our understanding of cosmic structure on its head. Imagine the universe not as an expanding void, but as the interior of a black hole so vast its curvature is imperceptible to us. The galaxies we see, the cosmic web we map, they might not be independent objects at all, but shadows. Projections of quantum information smeared across the black hole's surface, like a hologram where the image appears three-dimensional, even though the data encoding it lives on a flat screen. This idea, known as the holographic principle, suggests something staggering. The universe's true structure isn't in the space around us, but encoded on a distant boundary we can never reach, the cosmic equivalent of a black hole's event horizon. Every interaction, every particle, even the passage of time could be a translation of data flickering at the edge of existence. Think of it like a video game, The lush, three-dimensional world you explore isn't rendered all at once. It's generated in real time based on code stored elsewhere. In this cosmic version, the code is written in quantum bits on the universe's outer shell, and what we experience as reality is just the projection. Now, here's where it gets even stranger. If the universe is a black hole's interior, its expansion might not be due to dark energy alone. It could be the slow-motion evaporation of the black hole itself. Hawking radiation, the faint glow that causes black holes to lose mass over eons, might manifest on our scale as the relentless stretching of space, the galaxies racing away from us. They're not just drifting, they're riding the tide of the black hole's gradual dissolution. This would mean the universe's fate isn't just a question of dark energy strength, but of how quickly the higher dimensional black hole that birthed us is fading into nothingness. Evidence for this radical idea might already be hiding in plain sight. The cosmic microwave background, the afterglow of the Big Bang, shows patterns that some theorists argue resemble the chaotic fingerprints of quantum data on a black hole's horizon. Even the universe's large-scale structure, with its intricate filaments and voids, could reflect the way information scrambles and spreads across a black hole's surface. Simulations of black hole interiors reveal turbulent, fractal-like geometries that eerily mirror the distribution of galaxies in our own cosmos. It's as if the universe's blueprint was drawn in quantum ink, and we're only now learning to read it. But the most profound implication isn't about scale or structure, it's about meaning. If the holographic principle is true, then searching for the edge of the universe is futile. There is no edge, at least not in the dimensions we perceive. The true boundaries lie in a realm we can't access, where the data that constructs our reality is stored. The night sky, with its swirling galaxies and glittering stars, becomes a grand illusion, a mirage woven from information we'll never directly see. And if that's the case, then the greatest cosmic mysteries, dark energy, the Big Bang, even the nature of time itself, might not be solvable by staring deeper into space. The answers could be written in a language of quantum bits, waiting at the horizon of a black hole we're already inside. So the next time you look up at the stars, consider this: you might not be gazing out into the universe at all. You could be peering inward into the depths of a singularity's shadow, where the true nature of reality lies encrypted on a boundary as distant as it is invisible. And if we ever crack that code, it won't just change how we see the cosmos, it'll redefine what it means to exist within it. Quantum entanglement is often called spooky action at a distance. For a reason, particles linked in this bizarre quantum dance can mirror each other's states instantly, whether they're inches apart or separated by entire galaxies. Now, imagine that same eerie connection operating on the grandest scale possible, weaving invisible threads between distant corners of the newborn universe. This isn't just a thought experiment. Some cosmologists propose that entanglement didn't just happen between particles. It might have tied together entire regions of space, orchestrating the large-scale structure of the cosmos in ways we're only beginning to unravel. Picture the universe in its first moments, a seething quantum foam where particles flickered in and out of existence. Normally, these fluctuations would be random, chaotic. But if entanglement stretched across the cosmos, it could have synchronized them, creating subtle correlations in the density of matter that eventually grew into galaxies and clusters. Think of it like a cosmic game of telephone, where whispers exchanged between entangled regions echoed into the patterns we see today. The cosmic microwave background, the afterglow of the Big Bang, might hold the first clues. Tiny temperature variations in this ancient light could betray where these quantum handshakes once occurred, like fossilized imprints of a hidden quantum network. The implications are dizzying. If entanglement helped shape the universe, it would mean the cosmos didn't just evolve under gravity's slow pull. It was choreographed from the start, with particles conspiring across unimaginable distances to create the cosmic web. Recent simulations show how entangled quantum fields in the early universe could have generated the precise statistical patterns we observe in galaxy distributions, almost as if the universe's blueprint was written in quantum code. Even more radical, this could solve a long-standing puzzle: why distant regions of space, too far apart for light or influence to have ever connected them, look so eerily similar. Entanglement might have synchronized them before the cosmos even finished inflating, but here's where it gets truly mind-bending. If entanglement sculpted cosmic structure, it challenges our most basic notions of cause and effect. Normally, nothing can travel faster than light, let alone instantly link events across the universe. Yet entanglement defies that rule, suggesting that space-time itself might be secondary to some deeper quantum layer of reality. Some theorists even speculate that the cosmic web's filaments and voids aren't just shaped by gravity, they're shadows of an ancient quantum entanglement network frozen into the geometry of space. The hunt for proof is already underway. Telescopes are mapping the universe's structure with unprecedented precision, searching for statistical anomalies that could hint at quantum correlations imprinted billions of years ago. Others are probing the cosmic microwave background for signatures of primordial entanglement, subtle deviations from randomness that no classical process could explain. If they find them, it wouldn't just reshape cosmology. It would reveal that the universe's grand design was written not just in the language of gravity, but in the silent whispers of particles that knew each other's secrets before time began. So the next time you hear about quantum weirdness, remember, the spookiness isn't confined to lab experiments. It might be etched into the very fabric of the cosmos, a ghostly hand that guided the birth of galaxies and the fate of everything we see. And if that's true, then the universe isn't just stranger than we imagined. It's stranger than we can imagine. Deep in the heart of the cosmos, something unseen is tugging at thousands of galaxies, including our own Milky Way, with a force so immense it defies explanation. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it's dragging entire galactic neighborhoods toward it at over 2 million kilometers per hour. But here's the catch: we can't see what's pulling us. Hidden behind the dense star fields of our galaxy's central plane, this cosmic enigma remains shrouded in mystery, leaving scientists to wonder whether it's a colossal supercluster, a gap in our understanding of gravity, or something far more exotic lurking in the shadows of the universe. At first glance, the Great Attractor seems like it should be straightforward, a massive concentration of matter exerting gravitational pull, like a celestial magnet. But when astronomers mapped the region using infrared and radio telescopes to peer through the Milky Way's obscuring dust, they found something puzzling. The Norma Cluster, a rich gathering of galaxies near the suspected epicenter, is massive but not nearly massive enough to account for the observed motion. It's as if we've stumbled upon a cosmic crime scene where the fingerprints of gravity don't match the suspect. This inconsistency has led to wild theories, including the possibility that the Great Attractor isn't just a cluster at all, but a fossil relic from the universe's most violent infancy. One provocative idea suggests it could be a remnant of a phase transition, a moment in the early universe when space-time itself underwent a sudden shift, like water freezing into ice. Just as cracks form in ice as it solidifies, these cosmic defects could have left behind wrinkles in the fabric of reality, regions where gravity behaves anomalously. If such a defect exists in the Great Attractor's direction, It would warp spacetime in ways that mimic the pull of invisible mass, explaining why we measure such a powerful tug without spotting a proportional source. Simulations of the early universe show how these defects could form vast, invisible gravitational wells, trapping galaxies in their sway over billions of years. Yet the plot thickens when we look beyond the Great Attractor itself. Recent observations reveal our local galactic flow isn't just moving toward this mystery, it's part of an even larger current, pulled toward an incomprehensibly massive structure called the Shapley supercluster, over 600 million light-years away. This raises a haunting question. Is the Great Attractor merely a waypoint in a far grander cosmic conveyor belt? Or does its pull hint at something even stranger, like a flaw in Einstein's theory of gravity itself? Modified gravity models propose that on the largest scales, gravity might strengthen subtly, creating phantom flows that mimic the effects of unseen mass. If true, the Great Attractor could be the first clue that our understanding of the universe's fundamental force is incomplete. The key to unraveling this mystery lies in precision mapping. Upcoming projects like the European Space Agency's Euclid telescope aim to chart the distribution of dark matter with unprecedented detail, searching for hidden mass concentrations or distortions in spacetime that could explain the anomaly. Meanwhile, studies of galaxy motions are becoming so precise that even slight deviations from predicted paths could reveal whether we're dealing with a concealed supercluster, a relic of the Big Bang, or a crack in the laws of physics as we know them. What makes the Great Attractor so compelling isn't just the puzzle it presents, it's what solving it would mean. If it's a cosmic defect, it opens a window into the universe's earliest moments, when reality was still settling into its current form. If it's a sign of modified gravity, it rewrites the rules that govern the cosmos. And if it's simply a hidden concentration of matter, it forces us to confront how little we truly see of the universe's underlying structure. One thing's certain: as long as the Great Attractor keeps pulling, we'll keep searching, because the answers it holds could reshape our understanding of everything. What if the cosmic web isn't just a natural structure, but the visible seams of a vast, artificial simulation? The simulation hypothesis, long relegated to philosophy and sci-fi, is now being scrutinized through the lens of astrophysics. If our universe is a digital construct, then the distribution of galaxies, the geometry of voids, even the mathematical constants governing reality might not be fundamental at all. They could be artifacts the equivalent of pixels in a cosmic video game, with glitches and shortcuts betraying the underlying code. Take the unexpected symmetries astronomers occasionally spot in galaxy surveys. Certain large-scale structures appear oddly mirrored or arranged in mathematically precise ratios, as if generated by an algorithm optimizing for efficiency rather than randomness. In a simulated universe, such patterns might emerge from computational constraints, the need to conserve processing power by reusing templates or simplifying calculations. Think of it like a video game rendering distant mountains as low-resolution textures to save memory, only for sharp-eyed players to notice the repetition. If the universe operates similarly, these cosmic copy-paste effects could be the equivalent of a programmer cutting corners. Then there's the matter of numerical anomalies. The fine structure constant, which dictates how light interacts with matter, appears eerily fine-tuned for complexity. But what if it's not a law of physics at all? It could be a parameter set by the simulators, a variable tweaked to allow galaxies and ultimately life to exist. Even more telling are the occasional reports of this constant varying subtly across space, as if the simulation's code isn't perfectly uniform. These discrepancies, though controversial, align with the idea of a universe built on imperfectly patched-together algorithms. but the most tantalizing evidence might lie in the cosmic microwave background. This afterglow of the Big Bang isn't perfectly random. It contains faint, concentric circular patterns that some theorists argue resemble the artifacts of a reset in the simulation, like a universe that's been rebooted or debugged. Other anomalies, like the infamous axis of evil, a mysterious alignment of temperature fluctuations that defies standard cosmology, could hint at a coordinate system baked into the simulation's architecture. It's as if we're peering through the cracks in reality, catching glimpses of the scaffolding holding it all together. Of course, the simulation hypothesis isn't without its critics. Many scientists argue that apparent anomalies can be explained by statistical flukes or gaps in our understanding of physics. But the real value of this idea isn't just in proving we're living in a simulation, it's in the questions it forces us to ask. If we search for glitches in the cosmic code, we might uncover entirely new physical principles or hidden layers of reality. The hunt for simulation-like patterns has already led to discoveries about quantum gravity and information theory, proving that even outlandish ideas can sharpen our scientific tools. So whether the universe is a simulation or not, the hypothesis serves a deeper purpose. It reminds us that reality might be far stranger than it seems. And if we ever find irrefutable proof of a cosmic programmer, it wouldn't just rewrite cosmology, it would redefine existence itself. Until then, the universe keeps its secrets, leaving us to wonder if the galaxies above us are celestial bodies or just the shimmering pixels of a reality we've yet to fully decode. What if dark matter isn't missing at all, but a cosmic mirage, an illusion created by the universe's hidden geometry? This mind-bending idea challenges everything we think we know about the invisible scaffolding of the cosmos. Instead of invoking mysterious particles, some physicists propose that dark matter's gravitational effects arise from space-time itself being fundamentally uneven, like a crumpled sheet of paper distorting the path of rolling marbles. On the grandest scales, the universe isn't smooth, it's fractal, with matter clumping in hierarchical patterns that repeat from galaxies up to superclusters. And this very lumpiness could trick us into believing there's more mass out there than we can see. The math behind this is staggering. Einstein's general relativity assumes space-time is relatively smooth at large scales, but what if it's not? Imagine gravity propagating through a cosmos riddled with invisible folds and wrinkles, like sound waves echoing through a labyrinth. In such a universe, the equations we use to calculate galactic rotations and cluster dynamics would subtly misfire, requiring us to insert phantom mass at dark matter to balance the books. But the truth might be far stranger. We've been mistaking the curvature of space-time for matter. Supercomputer simulations show that fractal geometries can reproduce the observed motions of galaxies without dark matter, as if the universe's hidden topography is doing the heavy lifting. Here's where it gets even more radical. If dark matter is an emergent property of spacetime's structure, it would explain some of cosmology's most nagging inconsistencies. Take the bizarre behavior of certain dwarf galaxies, where dark matter seems to cluster differently than predicted. In a fractal universe, these anomalies wouldn't be glitches. They'd be natural outcomes of local spacetime geometry. Even the cosmic web's intricate filaments could be shadows of this deeper fractal order, with voids and knots arising not just from gravity's pull, but from the way reality itself is pleated at scales we're only beginning to map. But the real bombshell, this idea bridges the gap between quantum physics and cosmology. At tiny scales, quantum mechanics suggests spacetime is frothy and chaotic, like a bubbling foam. If that foam persists even at galactic distances, it could mean dark matter isn't a substance but a side effect, a statistical ghost emerging from the universe's granularity. the same way temperature emerges from the motion of atoms. Telescopes might soon find evidence by spotting subtle distortions in how light bends around galaxies, betraying spacetime's hidden texture. So the next time you hear about dark matter, remember, the answer might not lie in some elusive particle, but in the universe's bones, twisted, fractal, and far stranger than we ever dreamed. And if that's true, then the cosmic web isn't just held together by gravity. It's woven into the very fabric of reality, a tapestry whose threads are the folds of spacetime itself. Now consider this unsettling possibility. What if you, the galaxies around you, even the entire cosmic web you're observing, aren't real in the way you think? Enter the Boltzmann brain paradox, a thought experiment so bizarre it undermines the very foundation of how we perceive reality. Named after the 19th century physicist Ludwig Boltzmann, the idea stems from a simple but dizzying premise. In an infinite universe governed by entropy, random fluctuations can theoretically conjure anything, even a fully formed, self-aware brain, complete with fabricated memories of an entire lifetime. Given enough time, the chaotic dance of particles could spontaneously assemble not just a brain, but entire galaxies, stars, and planetary systems, all as fleeting statistical accidents in an otherwise disordered cosmos. At first glance, this seems absurd until you run the numbers. In a truly infinite universe, every possible configuration of matter, no matter how improbable, becomes inevitable. The odds of a Boltzmann brain popping into existence are astronomically low, but multiply that by infinite time and space, and suddenly, the improbable becomes unavoidable. The paradox forces a chilling question. Is our ordered, structured universe the rule, or are we the exception? Could everything we see, the elegant spiral arms of galaxies, the delicate balance of cosmic constants, just be a temporary blip in an ocean of chaos, a mirage of order destined to dissolve back into randomness? The implications ripple through cosmology. If Boltzmann structures are possible, then our most trusted observations, the uniformity of the cosmic microwave background, the accelerating expansion of space, might not reflect fundamental truths at all. They could be localized glitches, like a single coherent sentence appearing in a library of gibberish. Some theorists argue this undermines the scientific method itself. If reality might be an illusion, how can we trust any measurement or law? Others counter that the very stability of the universe, with its consistent physics over billions of years, makes Boltzmann scenarios vanishingly unlikely. After all, if random fluctuations could spawn brains, why not entire civilizations? Why does the cosmos exhibit such persistent structure rather than dissolving into noise? Yet the paradox refuses to die quietly. Modern physics grapples with it in unexpected ways. Quantum field theory suggests that even a vacuum isn't truly empty. It's a frothing sea of virtual particles flickering in and out of existence. Could these fleeting quantum events scaled up birth Boltzmann structures? Holographic principle theories add another layer. If our universe is a projection from a two-dimensional boundary, perhaps what we perceive as random fluctuations are computational artifacts, glitches in the cosmic code. Even the multiverse hypothesis gets tangled in the paradox. If infinite universes exist, then somewhere, a Boltzmann brain is indeed contemplating its own improbable existence, wondering if it's real. The real value of this paradox isn't in proving we're illusions. It's in exposing how fragile our assumptions about reality truly are. Every time astronomers map the cosmic web or physicists probe the Big Bang, they're implicitly betting that the universe obeys consistent, knowable rules. But Boltzmann's nightmare reminds us that certainty is a luxury the cosmos might not grant. Perhaps the answer lies not in dismissing the paradox, but in letting it sharpen our questions. If we're not statistical flukes, then what mechanisms enforce cosmic order so rigorously? What prevents the universe from devolving into chaos? The very fact that we're here to ponder these questions might be the best evidence that Boltzmann's ghosts are just that, ghosts. But in an infinite cosmos, even ghosts must find form somewhere, and that's a reminder to stay humble, because the universe's greatest trick might be convincing us it's simpler than it really is. What if the entire universe, every star, galaxy, and cosmic filament, is nothing more than a fleeting ripple in an infinite ocean of nothingness? The zero-energy universe theory proposes something astonishing. The sum total of all existence might add up to precisely zero. That's right, every joule of energy bound up in matter, every photon racing through the void, even the gravitational pull of superclusters, could all cancel each other out perfectly. Picture the cosmos as a cosmic ledger where the positive energy of mass and light is exactly offset by the negative energy of gravity's pull. In this view, reality isn't a grand creation from nothing. It's a perfect equilibrium where nothing ever truly existed to begin with. This radical idea stems from Einstein's own equations. When you calculate the energy of a gravitational field, it turns out to be negative, a counterintuitive result that suggests every massive object in the universe carries an energy debt. Stars, galaxies, even black holes might be thought of as positive balances on a cosmic spreadsheet, matched line for line by the negative entries of their gravitational fields. If you could sum every particle, every force, every curve of space-time, the final number might be zero. It's as if the universe borrowed energy from itself at the Big Bang, and everything we see is just the interest on that loan. So where do cosmic structures fit into this picture? Think of them as temporary wrinkles in the fabric of this perfect balance. Just as foam forms on the surface of a turbulent sea, galaxies and clusters could be quantum fluctuations in the zero-energy void, tiny pockets where, for a fleeting moment, the books don't quite balance. Gravity's negative energy dips slightly deeper in these regions, allowing matter's positive energy to briefly surge into visibility. Over billions of years, these imbalances grow, sculpting the grand cosmic web we observe today. But in the end, it's all just a temporary deviation from the ultimate equilibrium, nothingness. The implications are dizzying. If the universe truly has zero net energy, then the very concept of creation takes on a new meaning. There's no need for a mysterious source of energy to spark the Big Bang. The universe could have emerged spontaneously, borrowing nothing and owing nothing, because its total energy was always zero. Even dark energy's accelerating expansion fits eerily well into this framework, acting like a cosmic accountant ensuring the books eventually balance. As space stretches, matter dilutes, and gravitational fields weaken, the universe might be slowly settling back into perfect equilibrium, erasing the temporary structures that dot its surface. But the most profound consequence isn't about physics, it's about perspective. If we're just fluctuations in a zero-energy void, then the cosmos isn't a thing at all. It's a process, a fleeting dance of positive and negative that only appears substantial because we're caught in the middle. The galaxies we marvel at, the stars we study, even the atoms that make up our bodies, might be nothing more than shadows cast by a deeper symmetry, an eternal zero-sum game where existence and nothingness are two sides of the same coin. And if that's true, then every moment we spend gazing at the night sky isn't just an act of exploration. It's a glimpse into the greatest magic trick of all, a universe that conjures itself from nothing, holds itself in perfect balance, and one day might vanish without a trace, leaving only the quiet hum of equilibrium behind. Empty space is never truly empty. Even in the deepest void between galaxies, where matter is almost non-existent, the quantum foam of reality seethes with activity, virtual particles flickering in and out of existence so fast they defy measurement. This isn't just theoretical. In labs, we've caught glimpses of this chaos through the Casimir effect. Place two uncharged metal plates infinitesimally close together in a vacuum, and an invisible force pushes them together. Why? Because the plates restrict the types of quantum fluctuations that can exist between them, creating a pressure imbalance with the infinite fluctuations outside. It's as if empty space itself is alive, flexing its muscles in ways we can barely perceive. Now, stretch this phenomenon across the cosmos. What if quantum vacuum fluctuations didn't just operate on microscopic scales? What if they left fingerprints on the universe's largest structures? Picture the early universe, a turbulent sea of plasma and energy. Tiny density variations amplified by gravity eventually grew into galaxies. But here's the twist: gravity alone might not have been the only sculptor. Quantum fluctuations, those same phantom forces behind the Casimir effect, could have nudged matter into clumps and filaments, subtly steering the formation of the cosmic web. It's a staggering thought. The same ghostly pressure that moves plates in a lab might have helped assemble galaxy clusters over billions of years. The math hints at tantalizing possibilities. In regions where matter was already slightly denser, the vacuum's energy density could have varied, creating pressure differences that encouraged further collapse. Think of it like cosmic weather: high-pressure zones where quantum forces pushed matter together, and low-pressure voids where they let it spread thin. Simulations incorporating these effects show peculiar alignments in galaxy distributions, subtle patterns that pure gravitational models struggle to explain. Some theorists even speculate that dark energy, the mysterious force accelerating the universe's expansion, might be tied to these vacuum fluctuations on a grand scale. If true, the same quantum froth responsible for the Casimir effect could be shaping the universe twice over, first by seeding structure, then by tearing it apart. But the real mind-bender lies in what this means for nothingness. We think of empty space as passive, a stage for matter to play upon. The Casimir effect flips that assumption on its head, revealing the void as an active participant, a weaver of invisible forces. If these quantum whispers influenced cosmic structure, then the galaxies we see aren't just products of gravity and dark matter. They're the echoes of a deeper, more fundamental turbulence, a universe where even absence has weight. The hunt for evidence is already pushing the limits of observation. Telescopes mapping the cosmic web's fine details could uncover anomalies, strange correlations in galaxy orientations, or clustering patterns that point to vacuum forces at work. Meanwhile, tabletop experiments with ultra-sensitive sensors are probing the quantum vacuum's behavior under extreme conditions, searching for clues about how it might scale up. The answers could rewrite our understanding of everything from the birth of galaxies to the fate of the cosmos. Because if nothingness can shape the universe, then the line between something and nothing isn't just blurred, it might not exist at all. What if the universe isn't just governed by physics but by processing power? Imagine reality as a vast cosmic computer, where galaxies aren't just collections of stars, but intricate data structures humming with computation. In this radical view, the speed of light isn't just a limit, it's the processor's clock speed, the maximum rate at which information can travel across the cosmic circuitry. Black holes, they might not be mere gravitational pits, but the universe's memory sinks where information gets compressed, stored, or even erased. This isn't just poetic metaphor, it's a framework that rewrites the rules of how cosmic structures emerge, suggesting that the universe isn't just built on matter and energy, but on the flow of information itself. Think of the cosmic web not as a static scaffold, but as a dynamic network where filaments of galaxies act like conductive wires, transmitting information across unfathomable distances. Each interaction, every collision of particles, every warp in spacetime could be a computational operation, a bit flip in the grand program of existence. Even quantum entanglement, that spooky connection between particles, might be the universe's way of parallel processing, performing calculations faster than light by exploiting shortcuts in the code. It's as if the universe is running a simulation, not just metaphorically, but literally, with the laws of physics as its programming language. Here's where it gets even wilder. If reality is computational, then the structures we see, spiral galaxies, superclusters, even the voids between them, might be emergent properties of information dynamics. Just as a computer game generates forests and cities from algorithms, the cosmos could be rendering galaxies from underlying data. Some theorists propose that dark matter, that elusive invisible mass, might not be a particle at all, but a kind of cosmic REM, a background resource allocation that stabilizes the system, ensuring galaxies don't glitch out of existence. Even dark energy's accelerating expansion could be interpreted as the universe's memory filling up, forcing space itself to stretch to accommodate more data. Evidence for this idea isn't just philosophical. The holographic principle, which suggests all the information in a volume of space can be encoded on its boundary, aligns eerily with how computers store data on two-dimensional surfaces. Black hole thermodynamics, where entropy scales with surface area rather than volume, mirrors the way error correction works in quantum computing, and the universe's startling efficiency, its ability to pack maximum complexity into minimal rules, echoes the elegance of optimized code. It's as if we're reverse engineering the universe's source code, one cosmological observation at a time. But the most profound implication isn't about how the universe works, it's about what it means for us. If reality is computational, then consciousness might not be an accident of biology, but an inevitable output of the system's processing. Our quest to understand the cosmos wouldn't just be science, it'd be debug mode, a way for the universe to observe and optimize itself. And if that's true, then every time we map a galaxy or measure a quantum particle, we're not just explorers. We're active participants in the program, nodes in the cosmic network, running the universe's most important calculation, the one that asks, "What am I?" So the next time you look up at the stars, consider this. Those glittering lights might not just be suns. They could be servers in a celestial data center, humming with the computations that keep reality running. And if we ever crack the code, it won't just change how we see the cosmos, it'll reveal that we're not just living in the universe, we're part of its algorithm. From quantum seeds to holographic codes, these 23 radical concepts shatter our most fundamental assumptions about the cosmos. The universe isn't just stranger than we imagined, it's stranger than we can imagine. A tapestry woven from forces and phenomena that defy conventional logic. Dark matter's invisible scaffolding, primordial black holes lurking in the void, cosmic strings vibrating through spacetime like guitar plucks from the Big Bang. Each theory peels back another layer of reality, revealing deeper mysteries beneath. Take a step back and consider what this means. For centuries, we've mapped the heavens as if they obeyed simple, predictable rules. But the deeper we probe, the more the cosmos resists easy explanation. The distribution of galaxies isn't just random chaos. It's a frozen echo of quantum fluctuations from the universe's first moments. The voids between them aren't empty, they're dynamic arenas where phantom energy and unseen dimensions might be at work. Even the fabric of space itself could be a projection, a holographic illusion encoded on a distant boundary we'll never see. What's truly exhilarating is how much we don't know. Every anomaly, those two mature galaxies in the early universe, the great Attractor's unexplained pull, the eerie symmetries in the cosmic web, is a clue waiting to be deciphered. The James Webb Space Telescope's discoveries, the puzzles in quantum entanglement, the whispers of gravitational waves from collisions we can't yet explain, all of them are pieces of a puzzle we're only beginning to assemble. This isn't just science, it's a call to wonder. Whether you're captivated by the elegance of Mund-revised gravity or the audacity of the simulation hypothesis, these ideas invite us to rethink not just the universe's origins, but our place within it. Are we accidental witnesses to cosmic evolution, or part of a grand computational process? Is the multiverse generating infinite realities beyond our own, or are we staring into the event horizon of a higher dimensional black hole? The questions are as thrilling as the answers are elusive. So as we close this journey, remember, the story isn't finished. Each observation, each experiment, each bold theory brings us closer to truths that could rewrite everything. Maybe dark matter isn't what we think. Maybe time crystals pulse through the infant cosmos. Or maybe, just maybe, the universe is hiding secrets we haven't even thought to question yet. That's where you come in. Which of these ideas ignites your curiosity? Do you see the cosmic web as dark matter's masterpiece, or gravity's rebellion against its own rules? Could the universe be a simulation, or are we standing inside a black hole's shadow? Drop your thoughts below. The conversation is just beginning, and if you're hungry for more mysteries, hit subscribe. The cosmos has infinite enigmas left to explore, and together we'll dive deeper into the unknown. Until next time, keep looking up. The universe is far from done surprising.